Hello, in this presentation we're going to use definite integration to find the work done of a certain application and then compare the answer to other methods that we could use to also find the work done. Okay, so what we've got here is we've got a material experiences an extension when a force is applied to it. This can be expressed as Ex for extension equals E to the power of the force times 10 to the minus 3. What I will do on this presentation is I'll go through the definite integration part fairly quickly because it's fairly straightforward and I've already covered it in previous presentations that I've done. Okay, what I've got here is a graph of the exponential e that we've got here, e to the power of f times 10 to the minus 3. This is a common, as you'll be aware, e is the common Euler's number. So for example, e equals 2.718. Okay, so that's to the power of the force. So we'd have force plotted along here, basically an extension up here in this particular application, and we'd end up with this shape, and then we'd find the values between 2 points, and that would give us, definite integration would give us the area under the curve. Let's just have a closer look at this curve. This is a bit of a digression, but very quickly. So you've got E equals 2.718. So if it crosses the y-axis at 1, because if you've got E to the power of 0, okay, anything to the power of 0, as my students should all know by now, is 1. So it's 1, so it crosses at 1. And if you've got 1, that means that it's e to the power 1 is just E, so 2.718 is there. Okay, and what we've got here to the left is this shape here keeps going down and down towards the 0 in the y-axis. It never gets there. And this is what is generally known as an asymptote, or words to that effect. There's other ways of pronouncing it, but I would say asymptote. Okay, and what asymptote means is it keeps getting closer and closer and closer and closer to the 0, but never gets there. So it has an asymptote of 0. So it actually never touches it. It always just turns away and turns away and turns away, and basically it goes on forever, never touching it. So when you've got an exponential with Euler's number, well, any exponential, then the asymptote is always on the horizontal. Just for comparison, if we to have a look at the opposite function of this, which is the log, so a natural log, then we would get a different asymptote. I'll show you what I mean. A quick sketch. You've got a line there, a line there. In fact, let me put the line up here. So if I plot a log on there, so this is 0 here. This goes sort of like this. Okay, and the asymptote on a log is on this side. Badly drawn, but so it's a vertical asymptote. It's going towards 0 on the x, so you get a vertical asymptote in that situation. But anyway, we're not going to digress any further than that, so moving on. So we've got this question. So we've got that formula, the previous given formula. It says calculate the work done by the force from 150 newtons to 675 newtons. So it says perform this task by an analytical, in brackets integration, just to define it, what it means, method, and by a numerical method. So two different methods there. It also says compare your answers, but the two different methods. So the analytical method is to put that into more English, is to use a mathematical approach that gives you something like a precise answer, or can give you a precise answer if you go, as long as there's not too many decimal places. Okay, now a numerical method is where we use an estimation method, or the form something like an estimation method. So we actually do this all the time without even thinking about it. So for example, if you go to the shop and you want to buy a box of cornflakes, and you go to the till and they swipe the barcode and they tell you it's £1,000 or $1,000 or €1,000. You don't need to do any maths to work out that they've probably got the price wrong. There's something wrong somewhere, and in that you've done an estimation in your head. You've come to two conclusions. One, the price is wrong, and the other one is you haven't got £1,000, dollars, euros to pay it anyway. Okay, so that's a numerical method. Probably a better example is if you wanted to paint a wall in the house, you know what colour you want, you go to the shop, you choose the paint, you look on the tin and it says it'll cover let's say 15 square meters, and you know that the wall is roughly 10 square meters. So you know that the paint's got contains enough paint to paint that wall. You don't start analysing it and working out how thick the paint's going to be and working out precisely the area of the room and working out exactly how much paint you need. You just go with a rough estimation. That's sufficient for most things in life, but it's still an application of maths. Okay, so let's have a look at the method by integration. I think to start, what I'll do is I'll just put the formula that we're going to use on here for reference. So it's here. So we've got our extension is equal to E to the power of the force times, and I'm going to write this as times 0.001. Okay, rather than doing the times 10 to the minus 3 or times 1 to times 10 to the minus 3. Just write it like that. Okay, so I just want to digress again. I know it's one of my trademarks, but we'll just I'll just page to another page. Okay, I just want to clarify something with this. This formula is not, in my opinion, and I'm open to correction, if anybody wants to put me straight, that's fine. But in my opinion, this is not the correct equation for extension due to force. And if I look at the next slide, let me explain. So this is a typical, there's two shapes here, the black and the blue one. So the black is a typical extension curve for something in a material like steel, mild steel. And this is another one for something else, like concrete maybe, I don't know for sure. But you get different shapes for different materials. But the relevant thing is this bit here from 0 to here, there, and from 0 to here on this one is linear, and that's obeying what's known as Hooke's law. So the extension is proportional to the force applied, and then it actually springs back because of the elasticity of the material. And then after that it goes plastic, so it stretches, and you get a work hardening, and then it starts to get the work hardening stops working, so it stops getting work hardened, in other words, and then you reach a point where it just breaks. So there's no more force applied because there's nothing to pull on because it's snapped. Okay, so this is a typical shape. So you can see that formula we've got on the other page is nothing like any of this shape. Maybe this bit here. Okay, but anyway, that doesn't mean that we can't use it anyway and learn from it. You might say, well, Kevin, why are you using it anyway? Well, to be honest with you, it's because it's in one of the BTEC questions. And my students are doing BTEC, so it's convenient that I covered it in a similar shape to what they've got there. Okay, so moving on. So I'm going to do this bit fairly quickly because, as I said, we've already covered definite integration, but we've got this. So the work done, let's just go back to this. The work done is the area under the curve. So say we're doing it from here to here. That there, it's supposed to be shaded in, okay, would reflect the work done. That's a standard thing to do with extension. It's actually stress and strain on an object. So that's the work done from that point to that point there, which fits in lovely with our integration. Okay, so we've got, so what we're saying is the work done is the integration from 150, that's come from these values up here, 150 newtons to 675. Okay, of our function, which is e to the f. I'm going to put the 0.01 in front. That's more of the standard layout, times the force, and it's in relation to the force. Forces are a quantity that's varying. Okay, so if I do the definite integration of that, remember that when we do the differentiation, the integration of this function, it becomes a divide. Let me show you what I mean by that. So we put the answer, when we're doing definite integration, we do it in square brackets. So we've got e, this all stays the same, because Euler's number when integrated or differentiated stays the same. Okay, and we have a divide by the constant in front, which is our 0.01. Close the brackets. 150 to 675. Whoops. 675. Let's do that a bit neater than that. So, right, 675. Okay. Let's just move this up a little bit. So we've got next bit, where are we? Work done equals. So if I put these values into my variable f, with the so I'm going to do this in shorthand slightly. So we've got e to the, so if I multiply 675 by 0.01, I just move the decimal point 3 places basically. So I've got 0.675 I'll divide by 0.001 minus e to the 0. Same thing. Oh, dear me. .150. Obviously I don't need the 0 on the end. 150, and I'll divide by 0.001, and that gives me an answer of, so it's just a case of pulling it in your calculator, 802 point, it's 199, so I'm going to say 0.2. Okay, so that's the number to remember, that one there. So commit that to memory. Nearly forgot an important point there. What units are we in? Joules. Work done is in joules. So now what I'm going to do is I'm going to make use of a spreadsheet, put the formulas in, plot the graph, and this will give you a feel for what we're going to do, how we're going to solve it by a numerical method. Okay, so I'm going to go through this. Forgive me if you're an expert at Excel and you know all about this, but I'm going to treat this as from starting point as though you know nothing. Okay, so what we've got to do it from forces from 150 and down to 675. So the trick with Excel is let's go up in tens. We could go up in fives, but the list would be too long. So 160, arrow key down to go to the next cell. 170. Okay. Now if I select all these with the mouse, drag this down, and it automatically increments it. You can see the number there to the side of the cursor as it increments it, and we're aiming for 675, which obviously won't fit. Right, so what we'll do is we'll go to, oops, too far, 680. Okay, there, that's straightforward. Right, that's our first column. Second column, we're going to use our formula. So this is our exponentially to the force times 0.001. Okay, so the way to enter the formula in Excel is to hit the equals button key, and then we're going to use this. We're going to use the exponential of e, so it's exp. You'll see here in the code returns e raised to the power of a given number, so it's going to be in brackets. There's various tricks you can do with Excel. I've got to say Excel is really powerful for maths. So open bracket. Okay, so we've got the force, so we select cell which is B3, and you'll see it's put it in there. Hopefully this is big enough. Okay, B3, then it's multiply, so it's 0.001, close the bracket, and the best way to finish it is just to hit the enter key, and it gives us the answer. So it's done the sum for us. Okay, so exponential B3, which is 150 times 0.001. By the way, we use the asterisk key as the multiplier, or on the keypad it's there and there's an asterisk, so that represents the multiply. Okay, so that's straightforward. Right, now you might think that foolishly you've got to repeat that all the way down. Nope, because Excel is clever. All we got to do is go to that little corner there, it becomes a cross, we just drag it down. Here, presto. So we've got all the formulas now. So let's have a look at the next one down, and you'll notice it's automatically incremented the B3 to the B4. If we go down here, for example, increment to B10. So it is very clever. Okay, if I select all this data, like that, I can now put myself a graph in. So insert, I like the scatter ones myself. I need the points for the reason it'll become apparent, and I'm going to use the one that does the bits of bit curved lines. Okay, so there you go. Now that's too small to be any use to anybody, but don't with it. We'll just move it up here, go to the corner till you see the arrows, and drag it as big as you can get away with. Whoops, not that quite what I had in mind. Let's just go back a bit. Okay, go a bit more this way. Okay, so what we've got here is our values plotted. Okay, so this is all these values plotted. So we've got the force along the x-axis, and we've got the extension on the y-axis. Okay, so what do we do? Well, we've already worked out the area from here, from this one to not quite this one. This is 680. So there's the little thing we can do first. If we scroll down this, let's just change this 680 to 675, and you'll see it automatically changes this, and it automatically changes this, and you can see that that point there is closer. I hope you can see this. I hope it's all been captured. Okay, so what you would do is, so let's imagine we've got a line from here down to the x-axis, and a line down from here, and we want that shade that in, and we want that area, and that will give us the work done. So an estimation method is just to treat this as a straight line. So this is quickly going to give us a reference point to check our answers. An answer that we did from the integration is similar. So it's a quick, easy way. Now, if I just get back up my open board. Okay. I need another page. Okay, so what we can do, if we want to find the estimation of a shape like what we've got at the minute, so let's say we've got this. Okay, and we've got a shape like this, which slightly curves upwards. I've exaggerated the curve there a bit. We've got this point here to this point here, like that. Okay, let's go back to my lines. So we've got from there to there. Okay, so this area we're going to find. Now we need to know that, right, this, if we want to find that area of that shape, now it's just a shape. If you think about it, it's a shape, I don't know what you'd call that actually, four-sided shape. There's two ways of doing it. One is we can divide it up into a square and a triangle. Let's do this in a different colour. So we can treat that like that. Whoops. Where's my moving thingy? If it lets me. So I'm going to abandon it at that point. You know what I'm trying to say. That should be horizontal, but it's not. So we've got this area which is a rectangle, and we've got this which is roughly a triangle. So if we know this height here and this height here, we can start to work out. So we can work out this is that height times that distance there. That'll give you this area under here. And then I've got that difference from there to there times that distance, and then half of it because it's a triangle. Add them together and we've got a solution. So the question is, where do we get these values from? That one and that one. Well, we can do it with the maths, with the formula, just put the numbers in and that will give us them. But we've also got another thing to help us here. So if I just go back to my spreadsheet, here we go. One of the many great uses of Excel is if you go to the point there, I hope you can see that okay. So I hovered over there and it should, and it's not going to do it. Let's go over here. Try it. If I select it, that's better. So my point there, it says series 1.675, 1.96. Okay. And down here I've got series 1.150, 1.16. So basically all I've got to do is put them into a formula. I'll just go back to my other screen for that, put the formulas in, put those numbers in, and then take it from there. So back at our other slide, we can now let's just put some values on this drawing here. So we've got at this point, what did I say it was? 1.16, 1.62, and this one we've got 1.96. Okay. So there's actually two ways we can do this, but let's just start with the one I was on about before. So this square here is simply, this was 150, this is 675. So that means that difference from there to there is 525. So I can go, let me just shuffle up a bit and over a bit. Okay, so what I can do is say that this is here, this 525. So I can, if I go to find the area of this, it's 525 times that height there, 1.6, plus this triangle. So that's 525 again, the base, times, I seem to have gone back into blue, but never mind. And it's the difference from there to there divided by 2. So in other words, 1.96 minus 1.62 divided by 2 because it's a triangle. Okay, I can divide the whole lot by 2 if I wanted, it'll give me the same result. And that will equal, if I look at my notes here, that gives me 819. If you remember, our result before was 802.2. So I'll just put that in there, 802.2. That's our target value. Okay, so by this method of estimation, we've got 819.525 actually, 0.5, near enough. Okay, that's in joules as well. This is in joules. Okay, so obviously not the same answer, but if you think about it, we've treated this as a straight line when actually it's curved in, so it's going to be less than. So immediately it feels right. That's the first thing we can say about it. It feels right, so that's a good start. Okay, right, before we go any further, let me just quickly do another method. What we could have done, when you've got this shape, there's another formula for solving it, and that is to go to the middle point here. Okay, let's put a line on actually. Shall do that in a different colour. So say we've got a line, let's pretend that that's the middle. Okay, and find that point there. Okay, and we find that point there by adding that to that divided by 2. We just need a bit more space again. So what we get this time with this formula is the formula this time would give us the width times the height. It would be 525. Oh, it's always a good idea to turn the pen on. So 525 times, and then what we do, this is a slightly quicker, easier way, it's why I'm mentioning it, and it's going to become relevant for later on. 1.96 plus this time, notice the different signs because we're doing a slightly different exercise. What we're looking for is the height of that middle point there. Okay, so 1.162, divide that by 2. Okay, so that gives us that average value, and that gives us, what would you believe, exactly the same answer. Of course you would believe, because it's the same thing, just a different way of getting there. 0.5 joules. Okay, right, now let's just go back a little bit. Now the important point here is, very inaccurate of course, but what happens if we decided to divide this up? We divided this into, they treated this as one whole one. I know we went to the midpoint, and that's actually called the mid-ordinate rule actually. What happens if we divided it up again? So let's say we divide it into halves again. Whoops. And then again. Oh dear, I can't draw a straight line, and again, and so on, and so on, and so on. And then we treated these as the mid-ordinate rule, so use this method. We'd actually get closer and closer to 802.2. So what I'm going to do is I'm going to do another video after this one, and it's going to be how to do this in Excel. In Excel you can't do integrations, but we can use this mid-ordinate rule to find a solution that's fairly close, as you'll see. So that'll be my next video that I do. So thank you for listening, and I hope it's been of use to you.